Thanks everyone for coming to this talk. My name is Gabby Shklovsky. I work for Revenue Analytics based in Atlanta, Georgia. And just a little bit about us. We're a tech-enabled consulting firm that helps some of the world's biggest companies make their biggest revenue decisions, such as what to charge, what to stock, and what to promote when. So obviously in helping companies make those decisions, machine learning, predictive analytics are a big part of that. And that is what kind of brings our interest to random forests. And kind of from my motivation for this talk was I've seen random forests become a lot more popular over the past several years, and there are tools, great tools like scikit-learn, which makes it really easy to get started with kind of just dumping your data in and seeing what happens. But I've also seen a lot of kind of colleagues and friends that try this, and it just don't get great results when you just kind of do that, let me dump my data into this model and see what happens. So just wanted to kind of share some best practices that I've learned over the years that can hopefully be helpful to others as well. So our agenda here, I'll just start with a brief overview of what random forests are, then get into some best practices for training them, where the idea is kind of how do we get the best predictions possible from the data available, and then spend a lot of time getting into best practices for interpreting random forests. So aside from our typical kind of accuracy metrics and whatnot in machine learning, how do we interpret the results coming out of random forests? So things like sanity checking model outputs and kind of breaking inside that black box to provide insights to skeptical business leaders. So let's get started with that random forest overview. So at a high level, random forests are a type of machine learning algorithms known as ensemble methods. So ensemble methods just use multiple machine learning models which together give better predictive performance than any one component would on its own. And random forests are just ensembles of decision trees. So the idea is you would train multiple tree models and you blend the predictions of each to determine the combined predictions. So kind of a parallel set of trees that you kind of combine to get a single prediction. And random forests are considered to be black box models, which just means that they have a complex structure, not necessarily easily interpretable to humans. But as I'll get into a little later, the fact that they do have this underlying tree-based structure does allow for at least a little bit more human interpretable insight than maybe your typical black box algorithm. And then, of course, one of the kind of big questions you get is, well, what's so random about them? Why is this randomness important to a random forest? And if you think about, kind of as I mentioned, it's a collection of decision trees, but decision tree algorithms are deterministic, which means that if you have a single input data set and you feed it into a decision tree algorithm, you're always going to get the same tree back. So if we just took that same data, plugged in 30 times, we're going to get 30 identical trees. That's not really helpful. We're not getting any value out of that. So we need randomization to produce ensembles of trees that are each somewhat different. And so random forests typically use randomness on two dimensions. The first is random sampling of data. So this is probably the more obvious one. This is typically done using bootstrapping, which is sampling with replacement. So the idea is now instead of having 30 trees trained on the exact same data set, they're now each trained on slightly different data sets. And that allows each tree to fit to slightly different patterns in the data that it's seeing. So you would get kind of slightly different results in each. And the second way randomness is incorporated is in the random sampling of possible split variables. So this is slightly more nuanced. So if you think about how a tree works, so you can look kind of at this tree model on the left, is at each node, at each level in the tree, it is choosing among all of your predictors to say which variable will give me the best split and where should I split it. So in a typical decision tree, like the one on the left, let's say we had 4 predictors in the model: customer type, number of employees, sell amount last year, and region. The decision tree algorithm will decide, hey, I get the best split if I split on number of employees at the value of 1,000. And that will basically iteratively do that at every level in the tree, and that's how it builds out the tree. Whereas what we do in the random forest to kind of bring in this randomness is you randomly restrict this set of potential split variables. So we can see on the right, we've eliminated number of employees and sell amount last year as candidates. We restrict ourselves to only 2 predictor variables as options, and then choose the best among them. So what that kind of does is it disrupts that greediness of the split variable selection. So instead of just kind of optimizing for each node each level of the tree. We're just injecting a little bit of randomness. Maybe by splitting on customer type, we get a little bit worse fit at the next level, but we could actually get a better fit a few levels down. Conversely, we could just get worse fits all the way down. And that's why we want to build multiples of these trees and blend them all together to get the best predictive result. So that kind of at a high level is random forests and what is random about them. And now we can start getting into what are our best practices for training random forests. And when we talk about training, a lot of it has to do with structuring the model and kind of data prep. So best practice number one, which is a common thing I see a lot, is it's really important to factor out linear relationships between predictor and response. So a random forest is a collection of trees. Trees have a non-linear structure. It's a tree structure. If we have linear relationships within the model, it generally doesn't tend to perform well. A tree will try to approximate something that is linear, and that's just not a great thing to do. It'll overpower subtler effects that we might be more interested in learning about. So we want to kind of stick with the idea of let each model do what it does best. If you have parts of your problem that are linear, hey, let's just go ahead and use a linear model for those parts. If you have parts that are nonlinear, well, hey, random forest might be a really great option for getting good predictive power for the nonlinear components. So to kind of highlight this, and I'll use this example throughout the talk, is just pulled some data for a B2B company that wants to predict customer spend next year. This is a company that's selling a product to businesses, and they have some data on what the customers have spent over the previous few years and some customer attributes, and want to kind of build some predictive models of what do we expect a customer to spend with us next year. That could be an important input for, let's say, their sales team of knowing, hey, who should we target to make sure like they're not going to drop us next year, or they're not going to spend less with us, where we're going to target our discounts, et cetera, et cetera. So that's kind of the problem we're looking at. And so to start, if we kind of just basically throw our data into a random forest model and use last year's spend as one of the variables to predict next year's spend, we'll see that the last year's spend will completely dominate our tree splits. So kind of I have a single tree on the slide here. What I did was fit a random forest with scikit-learn, I believe with 30 trees, and just randomly pulled one out and kind of plotted the result. And so because what a customer spent last year is highly linearly kind of related to what they're going to spend the following year, we see that the tree is basically just approximating that linear relationship. So kind of you see the first node split where sell amount last year splitting on less than or equal to about 42,000. Says, hey, if they spent more than 42,000 last year, they'll probably spend, we say they'll spend 65,000 next year. And if you go to the far left of the tree, if they spent less than 8,000 last year, we predict they'll spend 5,500 next year. So this isn't really adding a whole lot of new information. If you were to show this to your like sales executive, they'd be like, well, yeah, duh. I know that people that spent roughly 50K last year are probably going to spend roughly 50K next year. The ones that spent roughly 10K last year will spend roughly 10K next year. That's not really helping me. That's not adding a whole lot of value. What we really want to go after are some of those more second order effects that are more interesting. So we can get a better result by doing something as simple as changing the target variable to be a linear transformation. So we're now predicting sell amount difference, which is just the difference between sell amount, which is the variable we were trying to predict originally, and what a customer spent last year. So we're kind of internalizing that business intuition that, hey, we know people spend roughly the same amount year over year. But what I really want to know is that person that spent 50K last year, are they going to spend 51K next year or 49K next year? Because that's really going to inform how I'm going to approach that sales endeavor, how I'm going to think about pricing, how I'm going to think about how many resources to put into that relationship. So now with a new target variable, we get obviously a completely different model, a very different looking tree. So we see other factors now come through as predictive. And so all of these factors were included in the first model we ran. They just didn't actually show up in the tree. So we see customer type. So this data has customer types A, B, and C. So we see whether it's customer type A is important We see number of employees come through as important. And interesting enough, we still see last year's spend as predictive, but in a very different way. So if you look at kind of that second level on the left, when sell amount last year is higher, the difference tends to be larger than when it's lower. So maybe that's kind of a little different insight than what we learned in the original model. So kind of at a high level, having linear relationships kind of within your random forest and within your decision tree in general, probably not going to yield great results. So you really want to do is factor that linear relationship out. In this example, it was as easy as kind of just taking a difference, a really simple linear transformation. In other cases, it might make sense to run a simple linear regression as a first step and train your random forest on the residuals. That's kind of a paradigm that I've seen works really well. So that's the high level idea with this best practice number 1. But I just want to quickly call out one more thing, which is that R squared can be really misleading, especially in this case where we're comparing a model with a linear component versus one without. So if we were, what I'm calling model A, which is the first one with a linear piece, model B was the second one where we use the difference. We see for model A, the R squared was 0.86. So if you were naively just running this model and all you were using was R squared to evaluate it, you'd be like, this is a great model, I'm done, let's move on. And maybe if you saw that really low R squared of 0.01 for model B, you'd be scared and say, hey, I'm giving up on this, let me try something else. But if we actually look at other accuracy metrics like MAPE or mean absolute percent error on our final prediction, we see that model B does a lot better than model A once we kind of apply that transformation to get the actual target value back. So just kind of a heads up, be careful with R squareds. I call it out, it's a scikit-learn random forest regressor.score uses R squared score. So if that's kind of your default scoring method, maybe consider other ones as well. So just kind of a quick heads up there. So now we can get into best practice number 2, which is that feature engineering is key. And I think this is kind of generally important for many machine learning methods, but kind of wanted to get into a few specific ideas. The first 2 I'll walk through briefly, and then the last one I'll highlight with an example. So number 1 is just use domain expertise and business knowledge as a guide. I work in consulting, so we spend a lot of time talking with our clients, learning about their business, really understanding how they think the world works, kind of understanding their intuition for how their business works. And so you really want to take those ideas and kind of think about how you can link them back into features. So if you are kind of talking to the business and they say, hey, I believe there's a strong relationship between these 2 things. Well, hey, how do we collect data on those things and either confirm or deny that exists, or how can that kind of inform our predictive modeling? The second one is to explicitly define interaction effects as new predictors. So this is something that is always done in linear regression models. People tend not to do as much with tree-based methods because you kind of have the idea that, hey, there's like this tree structure, maybe it'll split on variable A first and then split on variable B next. And that will implicitly give me kind of an interaction effect between A and B. And while that is true and that can work, it often doesn't work the way you expect. And that kind of comes back to the greediness of how these algorithms work, that it's really, when it's making those split decisions, it's treating each level independently. It's not thinking, hey, I should split on A now because I'm going to get a better result when I split on B next. It's going to say, no, I'm just going to split on C now because that gives me the best result one level down. So if kind of from your domain knowledge expertise, from your business knowledge, you strongly believe an interaction effect exists, hey, let's model that directly as a predictor. The other thing to note with random forest, kind of as opposed to your linear regression model, is that it does feature selection for you. So if you kind of include additional features that turn out to not be predictive, it doesn't really hurt your model. So kind of when in doubt, let's add some extra predictors. And that kind of links into the third point, which is using multiple metrics that are proxies for the same concept. So this is one I'll go into a little more detail with on the next slide with an example. But the idea is, hey, maybe you learn from your business knowledge that there's some concept that we believe is important and predictive, but we don't have any data to measure it directly. But maybe we have 2 or 3 different approaches that measure it indirectly. Instead of just picking one, again, like you would probably do in like a linear regression sort of setting, hey, let's just include all of them. So if we continue the example we were looking at before, but now want to add previous year spend difference as a predictor. So what we're predicting is basically the difference in spend between what we can say is year 1 and year 0. But we already know what the difference in spend was between year 2 and year 1. So if a customer kind of spent more the previous year, do we think they're going to spend more again this year, or maybe they'll spend less this year? So that can be kind of another predictor we add to the model. But whenever you're kind of thinking about differences, maybe you're thinking, should this be modeled as dollar or a percent? And so here it's like, why not both? Let's just add both the dollar difference and the percentage difference to the model. And the reason to do that, so one, it often leads to better predictive performance, because maybe we can kind of think about the tree structure that we have. Maybe in some regions of your domain, the percent is more predictive, and other regions, the dollar is more predictive. So kind of throwing them both in gives the model the option to choose either. What I've also found is it can kind of help you make your model less vulnerable to outliers. So let's say you have some new observation you're predicting, and it has a really large percent difference, but a smaller dollar difference because the denominator is small. Then maybe if you only trained using percent, you would get some kind of weird results in the output because it would kind of overfit to that, hey, it's a huge percent difference, that's weird, I'm going to give you a weird result out. Whereas you're training on both of them, maybe some trees will kind of train on the percent, some trees will train on the dollar, and that'll at least mute any impact you would get from having kind of a weird percent value. So this is kind of another, because again, we're dealing with like proxies for things, for like the true thing we're trying to understand. And some proxies may work better in some situations than others. So this kind of helps us prevent our proxy from being like an extreme outlier when in reality, the situation isn't really an outlier. And so the kind of data table I've shown here are our MAPE accuracy metrics for a few different variations in the model. So kind of model B was the one we looked at before. And then I included different variables in the model to see how the accuracy would change. So C and D each included just one of those variables, and we see the performance improves a little bit looking at accuracy. And model E includes both, and we get a slight improvement in the MAPE from 16.8 to 16.7. So in this particular use case, not a huge gain in predicted performance. In other cases, maybe you get a little bit more, but kind of that's the idea with this concept. So just kind of a quick review. Our best practices for training random forests. 1, let's factor out linear relationships. And 2, feature engineering is key. This is a place to spend your time really understanding the problem, really understanding your data to get the best results out of your model. And realizing that, hey, if you started using a linear type approach, just taking those same predictors and throwing them into the random forest may not give you the best value you can. Because kind of the types of predictors you might want in those different situations might be different. Okay, so that leads us into now best practices for interpreting random forests. So just a note here, like obviously a lot of what you're thinking about when you're evaluating models has to do with kind of the accuracy of the model and how well it fits the data. And there are tons of ways to approach that and lots of kind of literature out there on how to think about accuracy, so that's not what I'm going to focus on. I'm more going to focus on how you go about kind of interpreting the results of random forests, especially in the business context, where as much as executives will throw out all the big data machine learning buzzwords of I want this, I want that, at the end of the day, if you have a model that no one understands what's happening under the hood, they're going to be really reluctant to let you actually make decisions off of it, which kind of makes sense in a business context. So being able to get at least some interpretable output out is really important. So our best practice number 3 is relatively simple, just checking the feature importances and that those align with our expectations and intuition. So the feature importances kind of give you a measure of how important each of the different metrics are in adding predictive power to your model. So here's what I find really useful with this is checking, hey, are the features that are listed as important what you expected to be important? And if not, that's like a big red flag that, hey, I probably screwed something up along the way. Either my data is bad, it has missing values, or I did some transformation, I did it wrong, or I screwed something up with model fitting. If kind of something you expect to kind of pop out doesn't pop, that's just a really quick, hey, let me dig into this deeper and make sure I understand it, kind of regardless of what your accuracy metrics are telling you looks great. But if you kind of see something new and different you don't expect, and you go through and double check your data and double check your models and everything looks good, that can reveal some new business insight of like, hey, our salespeople don't ever consider number of employees of the company when they're thinking about who they should target and how they should price and all these different things. But this model is telling us like, hey, it seems to be pretty predictive. So, because that gives us a new insight that can kind of inform our business strategy. So yeah, kind of have this chart, but continuing the same example lists our feature importances for our model. But the thing that's really lacking from this is it's just telling you what is important. It's not telling you kind of why or how the number of employees variable is affecting our predictions. And so that brings us to kind of our best practice number 4, which is to check the directional relationship between top predictors and response. So I think this is a really key thing again for getting some interpretability out of the model and getting kind of your business folks, your non-technical people comfortable with what the model is doing, that not only do your accuracy metrics and whatnot look great, and not only are you really smart in telling them that like this is awesome, that when you put new data in, it's actually going to lead to good business decisions. And these directional relationships have a lot to do with that. So kind of have 2 approaches here, which I'll go into detail on both. The first is just to manually step through a few levels of the trees to detect patterns. So just kind of really simple, let's eyeball it and see what's going on. And then the second is to stress test the model with some synthetic data that varies the value of one predictor while holding all else equal. So the first approach is just manually stepping through trees. It's just a really great sanity check to, again, make sure there are no bugs in your data or your code or anything, and that the model just makes sense. So I took this Model E, which I think had like 30 trees. This is tree 0, just picked one out and kind of clipped it to the first 5 levels. And we can kind of just go and eyeball what the relationships are based on the splits. So the first feature was our sell amount last year difference percent. And if you kind of just look at that first split, when it splits to the left, which is a lower value, the value of the prediction is higher than when it splits to the right. And we see kind of that same pattern again, every time it splits, that we get a higher value to the, I guess we get different patterns at different levels. But kind of the high level pattern was the higher the sell amount last year difference percent, the lower the predicted sell amount. So this is kind of our regression to the mean idea that, hey, if someone spent a little bit more with you last year, maybe they'll spend a little bit less with you this year. Maybe that's an interesting insight. We can also look at number of employees. We tend to see when number of employees is higher, a lower predicted sell amount difference. So that, again, can be an interesting insight. And of course, this is a random forest. It's a collection of multiple trees. We want to make sure we look at least kind of 2 to 3 trees because you're going to see different patterns in different trees. So here I pulled out tree 6, just kind of randomly selected one. And we tend to see the same general trends at a high level, but it may look slightly different. So you may just want to check that you're not kind of overstating a relationship that isn't consistent across the board. So kind of eyeballing, manually stepping through those trees is always a great place to start. But it would be nice if we could see a little more systematically what the relationship is between the predictors and the response. So that's where this idea of stress testing the model can give you a more holistic view of particular relationships. So the idea is to create some synthetic data that varies one feature while holding all else equal. But we have to remember, because this is a nonlinear model, it's kind of an ensemble method, We need to use multiple all else equal data sets or else we could get misleading results. So you really want to think about this in comparison to like a linear regression model gives you, right, a single coefficient that is basically that directional, quantifies that relationship between your predictor and response. In a random forest, we're not ever going to get that single number. It's going to vary depending on kind of where we are. So I decided to first stress test sell amount last year difference in dollars because that didn't show up in the first few levels of our tree. And so the way I constructed this table was basically each line I selected 10 random rows of data from my holdout data set, which is what each one of those lines represents. And then kind of holding for each of those rows, held the value of everything else constant while just changing the value along the x-axis of the one feature we were looking at. So we can see that depending on the value of the other features, the level is certainly shifting across those different rows. But we do see a pretty consistent pattern in how it's varying along the x-axis. So we see it's relatively flat through the middle, and we see this decreasing relationship kind of above 4,000 or so. So that's kind of an interesting insight. We've at least kind of better quantified this relationship. We can kind of see the regions in which it's flat versus where it's negative. And so I did this again for the number of employees variable because that one was kind of a little more predictive and a little more interesting. And we see the chart looks pretty different. So again, each row is, each line refers to kind of one row from the holdout data set where we're holding everything else equal and just varying the number of employees. So we see kind of some, again, we confirm kind of that consistent negative relationship we saw before. But the size of that relationship is definitely varying depending on the value of the other data that we're considering. So kind of those top few lines are pretty flat. So depending on kind of the value of the other features for those, number of employees isn't that predictive. But kind of in the middle of the chart, it's very predictive, especially in this kind of inflection point we're seeing between 1,200 to 1,400 employees. So kind of that in and of itself, again, can be an interesting business insight of what is it when a company goes from 1,200 employees to 1,400 employees that leads to this huge difference in behavior, roughly all else equal, right? So at least within each line is kind of an all else equal. So that may be something where now you can go back to the business, to the sales team and say, hey, does this make any sense to you? And if not, let's dig into it. Let's talk to people. Let's understand the data better and understand what's going on. So this is kind of, I think, a really great approach for again, pulling a little bit more systematically that directional relationship out, knowing that you're never going to boil it down to like that single coefficient like you get in a linear model, but you can still kind of pull out some good insights with an approach like this. So just kind of to summarize, our two best practices for interpreting random forests were to start with our feature importances, make sure they align with expectations and intuition. It's a good way to make sure we don't have any errors in our code. And then best practice number 4, let's take it a little bit further and check those directional relationships. I think that's where you really get a lot of bang for your buck in terms of getting your business people, your non-technical people more comfortable with what these models are doing and kind of more willing to actually use them to drive business decisions. And so with that, I will open the floor at questions. Put my contact info at the bottom of the page so if I don't have a chance to kind of answer a question today, feel free to reach out, and I'd be happy to do so.
Does anybody have any? Thank you. Does anybody have any questions? You raise your hand. Okay, hold on. Mike's coming. Excuse me.
I don't need the mic.
Okay.
I'll be loud enough.
All right.
All right. So I love the visuals.
You got to be loud enough for the recording.
I love the visuals. What were you using for the graphics for the trees and the branches and the leaves?
Yeah. So
the question was, he loved the visuals and he wanted to know what you were using for the graphics on the trees and.
Leaf definition.
The definition.
These guys?
Yeah, these guys.
Yeah, so I did it. It's in scikit-learn using the export graphviz function, which I think you have to install like a third-party like GV editor.
It's like dot file
Yeah.
format.
Something like that. Yeah.
So you're using the same awful tree object. All right, cool.
Yeah, I was just checking to see if it was the same painful thing that I had to do, or if she found something better. So,
Nope.
it's the same painful thing.
Excellent talk, thank you. I was wondering if about the idea of removing the linear structure in the data. You showed this for a continuous outcome. Do you have any intuitions for when we're doing a classification task?
Yeah, that's a good thought. I have not personally worked with those problems as much, so I don't have kind of the personal experience to draw on, but I imagine you could get a similar effect. But yeah, it's especially in a case where it's like as simple as taking differences, which I guess you're not really going to get in classification. It's kind of really easy step. It just might be a little bit more of a transformation to do to factor that out.
So when you say holding all else equal in the context of your random forest example, like in linear regression, you could supplant, in the multivariate case, you put the means in, and then you perturb the variable of interest. Like in this particular case, are you basically, say you're trying to predict a particular thing, you just keep its other variables what they are, and then perturb that particular variable a lot?
Yeah.
That's the practice? Okay.
Yeah, so and this is kind of just to understand how the model is working and understand, trying to just isolate that relationship between just that one predictor and response.
Yeah.
And there are probably other ways you can do this, but yeah, I just kind of randomly sampled the data to get those kind of all else equal sets.
Okay, yeah. So the other variables that you're not interested in, you keep those as is, and then you fluctuate.
Yep.
Okay.
This is more of a high-level question around dealing with other businesses, because it sounds like in consulting you would know a lot more about this than I. When you're talking about interpretability and just using the models and having them deployed, or the businesses using them, do they ever ask about what happens when they start using the model and then their business changes, and then what happens to the model? Should they keep using the model? Should they call you back?
Yep. Yeah. That is definitely something we run into when you're basically trying to build models that are impacting business decisions, and kind of we deal a lot with kind of pricing, inventory. So these are things that are kind of definitely changing over time. Yeah, if you're doing your job right, you're gonna kind of eliminate most of the predictive power of your models over time, because you're gonna end up in like the self-fulfilling loop. And so kind of I think the best way we have of doing that is what I think we try to call like continuous learning, where you basically retain some sort of holdout set over the long term. So maybe 10% of the time you don't use the model and you just use whatever your old business practice was. And that way you can kind of keep retraining the model on that sliver of the business. Because if not, you could run into problems with the entire nature of your business has changed now that you've changed your business decision. So there's not a good solution to that problem, but that's probably, if you have a high enough transaction volumes, basically keeping kind of a holdout set where you're not applying the best strategy, and then use that for retraining the model.
Yeah, I'm just curious about what's the best way to create a synthetic data. For example, if you want to do some simulation study, using linear model, you can generate in randomly, and it's very obvious you can create a true model out of that. So if you want to, say, test some methodology, then you want to create some simulated data for random forest. How would you do that?
Yeah, so I'm not sure how you would create like the best synthetic data. Or my goal was more like let's just do something simple and easy that's going to get us close to what we want. That's generally the approach I'll take. So I'm not exactly sure. There are probably better ways you can kind of explore this, but my focus was, let's just do something simple and hopefully learn something from it.
So my question actually is like, how do you make sure your synthetic data is realistic of the real data?
Yep. So I think, again, I'll just come from just like kind of the business knowledge and understanding the data. So kind of and how I chose like the range of the X values. I looked at what have we seen historically and then widened it a little bit. So that was kind of how I did that. And then as far as the rows of data, I just randomly sampled 10 rows. You could theoretically sample a bunch more, and you could probably bootstrap and create more if you wanted to be really more precise. And it's just going to kind of depend on your underlying data, how much variation you would see in a chart like this if you were to kind of have more robust synthetic data versus doing something easy. Kind of because in this case, the random forests I trained weren't that deep, so there probably wasn't a whole lot more you're going to learn. But if you were training some more complex models that were really deep and had a lot of features, then yeah, having more robust synthetic data would be a good call.
We have one last question over there.
So my question is kind of on, since you probably use multiple variations of different variables, and random forest, say it uses like the square root of the number of predictors, you're obviously going to set some maximum depth as well. Maybe that ends up being, say, the number of predictors, square root of that, something like that. So do you find it best in order to like fine tune all those hyperparameters to kind of go ahead and run through the data, find that feature impact, and then cut out all of those variables and retrain on that main top subset? Or what are some of your practices on depth and also like the number of variables used at each split?
Yeah, I think so. Yeah, it's a good point around kind of at what stage in the process you train your hyperparameters. And so I think I tend to kind of take the first approach you described of I'm going to pick some reasonable parameters and do a lot of this sort of feature engineering, kind of experimentation, trying to get to a pretty good model that I'm confident in, and then kind of at the end, then kind of go back and do some more parameter tuning once I've kind of narrowed down the scope of, okay, I know for sure what my target variable is going to be, because that obviously can definitely change what the hyperparameters look like. I know more so, yeah, which features are actually predictive and kind of narrow down that scope and which all those different components. So yeah, I in terms of kind of that iterative cycle of experimentation, I find it easier to pick reasonable hyperparameters, do a lot of the experimentation, and then kind of go back and optimize them later.
Great, thank you.